Thank you, Mikhail, and thank you very much also for organizing such a beautiful school. Though it's autumn, but I think we are still in summer before winter starts, and it's a beautiful place as well. It's first time actually to come to Torun for me. I have come to Poland before, but not to Torun, and it's a beautiful town. I have been enjoying since then. So what Mikhail actually told me, not so much about the cavity, it's to give a bit of overview of the quantum hub. Or at least that's how I understood actually from him through his email, that somebody should speak about quantum hub in Birmingham. So my slide, I think what I have tried to do is mix with some sort of like information, but also a little bit of the work that we have been doing in Birmingham, especially on clocks. So it's a mix of informative as well as a bit of like telling what our group has been doing actually in Birmingham, particularly the group I lead in Birmingham. So first I will give you some overview of quantum hub for sensor and metrology that is being led by University of Birmingham. Actually, Professor Kai Bongs, who is the director of this quantum hub, who is also head of the group for cold atoms in Birmingham. So first I would say like what this is quantum hub about. So quantum hub is a consortium. If you really see, it's initially there were 6 university partners, but then with time there were more university partners which were added. Now there are 12 university partners, and additionally the National Physical Laboratory, and it has got support of roughly 200 industry partners in it. It was funded by, there was a program from the UK. It initiated in 2014, but it was announced by Chancellor at that time in 2013 in September that £270 million will be invested in quantum technology alone, and this is on top of what was the normal funding route that was going on in the UK. And so out of this 270 million, that was dedicated only to quantum technology for 5 years program at that time. And the idea was that there will be pillars in the UK, and these pillars will act as kind of like beacons for translating quantum science into quantum technology and through to market. So idea is, really goal was to build the science that has been achieved and realized using quantum principles. Then can we take that science to the market? And so the goal was to build a quantum industry in the UK, and that's why these 270 million pounds were given. There were some additional agencies like the STL, they also came along, and they also put some their own additional money, like they put something like within our hub 15 million. So that was our hub. So originally it was funded for something like 35.5 million for 5 years, but then the STL put another 15 million, so it became more like a 50 million at that time. Plus I'll give you some numbers very soon. So you could see that even at that time people in the UK, they thought that Europe, like triggered by what has happened in the UK in 2013 with the announcement of 270 million pounds into quantum technology, then Europe also started to think of that we need to initiate something which based on quantum science, that can we translate that science into technology and then make a market out of that one. And so into Horizon 2020, if you see it, UK started to think of EU can advance innovation based in quantum technology. And of course then they launched quantum technology initiative, and one of the projects, actually that's why this school is here, or partly that's why this school is here. So coming back to the UK, quantum hub, which is sensor and metrology led by University of Birmingham. So current status of that one is, now this phase, first will end 30th of November 2019, so roughly in few months from now, because it started 1st of December 2014. So what has been achieved? I think this slide summarizes by and large quite a few bullet points and the indices on which actually the measure or success is measured. So it is 202 collaborative projects with industry within this quantum hub. That's quite remarkable, I would say. 69 companies have invested money in some or the other form in this quantum hub. It originally started with 35.5 million from the government, which came through EPSRC, which is the main funding body for physics and engineering in the UK. Then it added another 75 million because there were other industries like Innovate UK that actually helps translate science projects or knowledge transfer to industry from academia, and including those values there was 75. So today this hub stands for more than 100 million investment into it after more than 4 years. It has created 50 jobs in industry because this is more about creating jobs, getting industry on board, engaging with them, and IP of course is also very important. More than 9 patents applications have been filed and 142 records of innovation. And you could see that there are, out of this quantum technology initiative, which was 270 million pounds, there were 4 quantum hubs actually that were set up. So one of them is this one, which is sensor and metrology. Another hub was in quantum computation. That's what I would call it. I think the name is NKIT, which is led by University of Oxford. Then there was another one which was more based on quantum information, and they do QKD type of work, and that is led by University of York. And the 4th hub, which was on quantum imaging, that's led by University of Glasgow. So there were these 4 pillars that actually were set up as part of this quantum technology initiative. And then there were skill hubs, because that was important not only just to push the technology and build technology and push through the market, but also develop skill, which means there were training programs for PhD and other set of things that were also set up. So total money that was invested in these 4 hubs was 120 million plus other initiatives that were taken as part of those 270 million. Then Innovate UK came along, and out of they launched many calls, and out of these these calls were mainly for quantum technology. And out of all of these calls, this hub alone got 44%, and I think that speaks how closely it works with industry, because these calls are led by industry, not by academia, but academia is important to be part of that one, and 44% of those calls came to this Birmingham hub. And you could see how it is spread. So this is UK map, and you could see Birmingham is somewhere here, and you could see of course South is much more engaged, but by and large I think this hub has been able to engage with partners across UK quite well. So this is I would say like this is just some sort of a very brief overview about this quantum hub. There is a new phase that is starting in actually December 1st. So it has already been announced, the money is already there. So this is additional money, I think total including phase 1 and phase 2, including industry participation, I think the number you can round up to 1 billion that UK will be putting into quantum technology initiative over 10 years. So idea is why this money, why this 270 million, and now of course Europe and Germany and many countries actually are putting a lot of money into quantum technology. Why this money? Why people are putting this so much money of taxpayers into this type of initiative? And the reason is, if you look at this is you could see resources means like just take academia or anywhere an idea, if you have an idea, and the resources that you need to realize that idea, and then this is more like stage of the development. So if you have an idea, then you are somewhere here, and then what you do is of course you go to a lab, or you take a page and paper, paper and pen, and then you start to think of that idea and you start to realize that idea. If you look at you are somewhere here, sometimes it's also called TRL level, technological readiness, because if you have just got an idea which is a basic idea, then you are here somewhere. So you require much less resources, but actually the number of resources that could be available to each is much higher. Actually is in this segment is the largest one that is available to you when you have just an idea which is at the level of where you just want to explore, a kind of a basic research you could call it. So the resource in terms of what you need, you have plenty of avenues where you can go to and try to really, I would say, look at the feasibility of that idea. But as soon as the ideas start to get mature and you want to say, okay, this idea is excellent and I would like it to go to the market, in the sense like I would like industry and also society to benefit from this idea, something should come out of this idea, then you could see that as you go through these different stages, the resources start to decrease. And then if you want to do some commercialization based on that idea which was here, you need more and more resources after some time. And so there is a valley of death. This is very famous valley of death, and this, most of the ideas, they are very good here, but by the time they go, it's, I would say, like you require massive investment, but probably not more than 10%, even in fact less than 10% ideas are able to make it to this region. So most of them die somewhere here, and that's why it is called valley of death, because there are no resources, or you have to find industry partner who is interested in it, or you have to set up your own industry. And so this is nobody, because industry thinks, if you are here, industry thinks, oh, it's too early, why should I invest? If you are here, or sort of like, I would say like, yeah, so what government thought is that there are brilliant ideas, and then what they can do is they can try to pump lot of money and then try to make a bridge based on this money, and then pull many of these ideas to this region. And that's where, and the idea is that industry, you could really attract industry based on, because they don't have to put their own money, it's the government money, and then they get more resources, and so somehow you are able to bridge this valley of death. And that's the idea why this 270 million has been put, and that's also the idea why Europe is putting 1 billion into it, and many other countries are putting 1 billion into it. Now, what was thought of at 4 years ago, or more than 4 years ago, roughly 5 years ago, within this quantum hub, I'm coming back to quantum hub, this is sensor metrology. If you look at the roadmap at the time, which was thought, it was around 2014, you could see here, and the roadmap was up to 2030, and of course things have evolved quite a lot since then. So the idea was like, these are novel physics ideas you could think of, that based on that one, something which is a laboratory based, which takes around kilowatt, many kilowatts, many times of power, and then it requires like this room full size, volume. They have already beaten, of course, many classical counterparts, for instance in terms of clocks, and there are many other sensors where either they are at par with classical or they have already beaten, and definitely they have much more potential than their classical counterparts. Can we pull them through in such a way that volume can be decreased? Let's say to start with cardboard size, instead of kilowatt, can we take them to 100 watt, so factor 10 reduction, and then 10 times better than their classical counterparts. And then of course you continue to pull through them, building upon these ideas which are novel physics ideas. Can we start to think of integrating them and then have industry which is based on quantum technology? And then of course at the same time as these things are pushing, technology is getting pushed, then we start to open the market, and then somebody start to really in industry start to sell them, or and then people start to use them. So you could say that you do market building on one side, and then you push the technology on the other side, but not only push the technology, you have to start thinking these systems. So what were the systems, or what were the ideas or themes which were considered in this quantum technology hub? These were, you could see, 5 main threats which were considered as part of this quantum hub. Gravity, like gravimeter, gradiometer, and it has a lot of applications in real world scenario. Then rotation, and these are based on mainly atoms. So this hub is by and large based on atoms, either hot atoms typically in case of I would say magnetic thread, otherwise cold atoms by and large. I think the largest activity in the UK within any hub based on cold atom, actually this is the hub. And then you have clocks, and this school is very much dedicated to clocks, so I would say a bit more about that one. And then magnetic sensing, I think there were lectures on magnetic sensing where it could be used for health sector. Quantum imaging, where a colleague of mine has been working on, where you could use quantum properties of light, for instance, to go down to a signal to noise ratio where you start to rely on quantum properties, essentially entanglement of photons. And then you could see that, of course, when you start to think of these different threads or different components, or you could say systems in this case, and then you need to start to think of what are these systems, if I call them systems, what are the components these systems require. And many of these, of course, systems require common components like optics, lasers, vacuum. And then, of course, you start to think of like you have built the supply chain, and I'll come to that one at some point more. And then first thing is you start to make a prototype. Like for instance, this integrated clock that we have, IQ clock, that actually we are working on making some sort of a prototype or industrial version of that one. And then industry takes it up, and then start to make a product line out of it. And then it goes to the market. And these are the application areas, for instance, in gravity detection of sinkholes. So if you have, like most of the time nowadays, what happens is if there is a sinkhole, let's say in a road work, they use conventional method, and many times they don't know actually where the sinkhole is, and they dig a hole at wrong place many times. And it also, the equipments they have, they take longer. So idea of quantum is that it can make things more precise, and it can make things faster, so you save money and you do things quickly. Rotation sensor, for instance, it could be very useful in case of navigation system, if you are building a navigator. Clocks, of course, clocks time is required everywhere. It depends what level of timing that you require, which is everywhere essentially. Magnetic, it was more for like brain diagnostics, health sector, or heart tomography. Quantum imaging, again, like biomolecules, for instance, you can start to think of, and or imaging other sort of stuff you could start to think of. So that were like kind of applications at the time that were thought of. So if you look at slightly bigger picture, why sensors? Why? Yes, please.
Question. So other applications like quantum computing, quantum simulation, quantum internet are of less interest at the moment in the quantum hub?
So like this.
Sensing applications?
So in this particular hub, it is focused mainly on sensor and metrology, not on quantum computation or quantum information, for instance. There are other hubs like led by University of Oxford. They are interested in that sort of thing. Quantum simulation, I think, has been part of Oxford hub to my understanding, but in the UK, it was more on the other activities. They focus more based on what was the strength in the UK. Yeah, but not in this hub. There is no work within this hub. So if you look at like slightly bigger picture, why sensor? Why people should bother about sensor? Because it's about like building industrial ecosystem, building an enabling ecosystem, and driving a quantum industry based on that enabling ecosystem. So if you look at why people should be interested in it, take anything, including like tractor in a field, to train, or to your mobile phone, or to your car. Everything is full of sensors. You know, even our body, like our ear, eyes, these are all sensors. And if you are able to build novel sensors, better sensors, and you can do things better than otherwise you are able to do, then what you can start to imagine it, even if you have a quantum computer or any computer, what it does is, if you want to get idea about that one, sensors are the one that provide you data, and then you can feed it and build your model or advance things or predict things, and then you can start to think of building an economy which is based on knowledge. But where this knowledge is coming from, you could see that sensors are the key to building such an economy, or to really get the knowledge out of the environment, including our planet, for instance. So based on sensor alone, there is an estimate that you can make an impact up to 10% of GDP. And when I say GDP, of course it could be UK in this case, but European GDP is very similar like UK, so you could make an impact as high as 10%, which means there is a potential of around 4 billion per year market based on the quantum technology, which is based on sensors. So there is a real, I would say, there is a real argument why these things should be done, and why these things are important, and why people have invested that level of money into it. Now, typically, like when we do research, like many of you probably are already doing PhD or would be doing PhD or have done, some of you, is we get typically the model that we follow in science is we apply, we write a proposal, go to a funding agency, and this funding agency typically gives us the money. Some funding agency asks annual report or certain level of reporting, but then we just continue to work in our lab or on our desk if you are theoretician, and then we try to really get some idea, and based on the proposal that we had put forth, and we try to get the results essentially at advanced knowledge and science. But here is different. So if you want to build a quantum industry, it has to be just beyond researcher. So you need to engage in a wider sense. So which means you have to consider that you within a lab, let's say you can build a technology, or you could do research. But if you want to take it to the market and to the society, then you need to make this bridge, and this bridge is not only one way, but it's actually both ways. So you need to have like engineers on board, you need to have end users on board, you need to think of like where is the appetite if something I'm building it. And so I think you need to take all the stakeholders on board, and that's when you make it change, and that's the idea of this quantum hub. And that's why you could see that there are so many industries where we have been able to engage. As I said, within this quantum hub, 5 years, and at the end of November 30 this year, and the new phase starts next 5 years. So in next phase also there is very similar thread that is part of this quantum hub, and new thing that probably has been added is terahertz radiation that comes from electrical engineers. They like to work with terahertz radiation, but otherwise I think scope has increased in the sense like now the second phase. In the first phase the demonstrators have been built, in the second phase is the application of those demonstrators in real world applications. So it is getting more and more into application domain this next five years. Because this school is dedicated mainly to time, to clocks, so I would spend some time on time. So within this quantum hub, I think within this quantum hub led by Birmingham, there is range of clocks which are being developed, and they range from 10 to the power minus 13 to 10 to the power minus 16 or better in terms of precision. So like from a relatively lower end of precision to highest end of precision. But remember, this is not about building the best clock, this is about building a clock which is useful in a given application, that there is an application that you can tackle, not inside the lab but outside the lab preferably, and that's the idea. So you have to shrink the size, you have to make it more robust, you have to make it field deployable, but range of these clocks, because there are different applications requiring different timing. Of course, if you have best clock in the world, you can use it for everything, but it could be overkill for certain applications and nobody will buy it. So if you look at it, it's the clock program within this Quantum Hub actually sits within a work package called work package 8. And just to give you a bit more information about that one, there is a clock based on cold atoms that is being worked on by University of Strathclyde. So where you use microwave transition of rubidium 6.4 gigahertz. Cold atom optical clock, which is based on strontium, that's the actually part I lead in Birmingham. It's an optical clock, compact lattice clock. Then there is a optical clock, but this is based on iron, that's led by Matthias at the University of Sussex. Then there are other portable clocks, for instance CGM clock, that is led by NPL and is also iron microwave clock based on ytterbium. So you could see that the range of clocks that are being actually tackled within this Quantum Hub, going from relatively lower end of precision to highest end of precision. Now just to give you a bit an idea in Birmingham, so we have currently 3 demonstrators we are actually engaged or have been working on. So this one is I shouldn't say much about that one. I think Raphael and many other people have said enough about it. So this is IKE clock, which is actually is partner within this school, which is funded through European FET flagship program. So idea there is that we build a transportable clock which is better than, actually it should be the other way sign, either equal to 1 part 10 power 16 or better, and the volume should be of the order of few hundred liter. I think the number that we used there was 700 liter, so of the order of 1000 liter actually. Then the clock that we crucially actually played a crucial role within, this is European consortium where there were other partners including actually Toptica within space optical clock program. It's led by University of Düsseldorf, Stefan Schiller, who is the coordinator of it. This is the idea there was to have something engineering model which could go one day to space and volume of the order of few thousand liters. So it's at the moment it's around 3000 liter, but I'll say more about this this setup. And precision to start with, it was 5 parts 10 to the power 17. So that was in minus 17 precision and uncertainty that was thought of at that time. And then the miniaturized lattice clock, which is part of Quantum Hub, again it's lower in volume, so roughly factor 10 low or more, actually order of magnitude low form factor, but the precision is of the order of 1 part minus 16 or could be better. So all these demonstrators that we are working on in Birmingham, they are based on strontium, as you can see, and I think I would not like to spend too much time, probably you have seen it enough. It's that you go through 2 stage cooling. One is broadband, one is blue cooling, and this is the first stage that you can use 1S0 to 1P1 transition and 30 megahertz, but you are limited in temperature. You can collect lot of atoms, but you are limited in temperature to few millikelvin, but then you transfer these atoms to the second stage cooling, which is around 7.5 kilohertz, and you can get a mode which is could be as cold as 1 microkelvin, for instance. And then once you are at 1 microkelvin, then you can trap these atoms in a 1D lattice, which is a magic lattice, and then you can do spectroscopy at 698 nanometer transition. So that's I think that's a standard approach that everybody has taken, and I have said it, but I say it again. So the idea actually in Birmingham that we have taken, there are 2 ways, broadly speaking. Yes, please. Yes. Yes.
Do you think, maybe you have some knowledge, if ISA Pathfinder project, I mean, is alive now after the last ISA meetings?
Yes, it is alive.
If you think so.
So far it is alive.
Okay.
As much as I know. But there was this meeting, big meeting in ESA. After that, I'm not so much aware.
Yeah, because I'm also.
Yes. No, this, no, yeah. So Stefan has not said much about it. But I believe it is still alive. So there are two, actually you can start to think of in terms of like optical clocks. There are two pathways you can broadly speaking now, because there is so much activity happening now. One is like you build the best clock, or you try to build one of the best clocks in the world, and you don't care about how much resources require, which means how much power it requires, how much space it requires, and how much volume it requires, but you continue to push precision and uncertainty of it. And there are a lot of groups, and that's how actually things started to start with. And then of course you use it for fundamental physics and also distribution of time. Then the another one that started relatively recently, I would say, like I would say arguably probably space optical clock program was the first one for optical lattice clock, which was transportable at the time or mobile at the time. And this is the path actually that's Birmingham has taken, and the idea is that you go vertically, which means without compromising on precision uncertainty, can we continue to decrease form factor, increase robustness of the setup, and miniaturize, of course. There are other groups which are also working on this one, and PTB is one of them, though PTB is part of this as well, but they have their own demonstrator, which is in a small truck and which has been functioning based on strontium. So this is just to give you a little bit the story about space optical clock. So this program started in 2010. Space optical clock 2, I would say there was phase 1, but at that time we were not involved because we didn't exist in Birmingham at that time, I think. And in second part, which was space optical clock 2, that's why you could see 2 here. So idea was that there are two engineering models that should be built. One is based on ytterbium, another is based on strontium. And ytterbium and strontium, both of them, the idea was that the precision and uncertainty to be achieved 5 × 10 to the power 17 should be achieved in both of these cases, and they should be engineering model, transportable, mobile, and should be precursor to taking something in space. To start with at International Space Station, and of course work is still going on. We are still working on that path, and that is a feasibility study funded by ESA, which is called ISOC. And so at that time, so we contributed significantly to the strontium part. So our contribution there was that we integrated this clock at the University of Birmingham. We also built its atomic package, computer control, and then we had to demonstrate its functionality and transport it to PTB, and then continue to characterize at PTB with the help of course other partners. So this was our involvement within this program, and you could see in June, 21st of June, we assembled it in Birmingham, showed it functionality. We had atoms in lattice at that time, and then we put it in MN, and then we withdraw at the time, and then it is now at PTB lab. It's still at PTB, and that's how the setup looks like. That's how it was, and within a couple of days, once the cables were put back, it started to function again. So I think that was quite for us an achievement. This is first time that something was built as complex, and then it traveled from the UK to Germany, and then everything started to work back. So that speaks about the robustness of the setup. It's around 3,000 liter, put everything together, including everything. So atomic package looks like that one. So it's 99 centimeter long and 45 centimeter wide and 60 centimeter in height. So it is on a breadboard, and so it's a mobile one. So here you have the atomic oven where you can heat. It's a designed atomic oven which idea came from Florence, and we adapted that idea into it. It's quite efficient one, very good oven that it works really well. And so you have the atoms coming out here, and then you have a Siemens slower which is based on permanent magnet. It was built by actually NPL, National Physical Laboratory in the UK. It's 28 centimeter, quite compact, didn't require any power. Then we built a very small vacuum chamber. Typically, you could see that almost any lab-based strontium experiment has water cooling, and it doesn't have any water cooling if you really see. And so these coils work 24 hours. I think it's around 10 watt power that has been limited to. So this is overall, except Siemens slower was built in Birmingham, and it works fairly well, I would say. So now, to start with, because strontium 88 has the highest abundance, which is 83%. So idea was, why not take advantage of the strontium 88, where we can get very good signal, and it's already there. But there were, of course, when you take the path of strontium 88, you have to start to think of that strontium 88 is a boson, and boson like to collide, which means they like to sit together. And then you also start to think of, if you build something based on strontium, the nuclear spin is 0, which means if you want to excite clock transition, you need to apply some magnetic field, and you also need slightly larger intensity of your clock laser as part of that one. And so which means that there are two challenges. One is like you have to start to think of Siemens shift that can limit your uncertainty in the setup, and because you have to apply larger intensity as part of your clock pulse, then you have to start to think of that it will also give light shift, and that will limit what is the uncertainty that you can achieve in your, typically at that time it was achieved, it could limit to 5 parts 10 to the power minus 15, in fact to minus 14 level. So which then look very attractive, because if you build a lattice clock and if your uncertainty is limited to minus 15 actually, so what's a big deal in it, or even less than that one. So it is a problem that you need to think of how to tackle it. The second thing is like, because bosons like to collide, they like to sit together, and that again can limit your uncertainty, which means like how good your clock could be, then again to minus 16 to minus 14 somewhere it could be. So again it didn't look very attractive. However, you can, without giving up, you can start to think of, let's say, oh, okay, it's a boson and I have a lattice. Yes?
So these strontium 88 doesn't have internal structure in ground state. So the collisions in ground state are highly suppressed.
There are, yes, yes. Yeah. It has already shown actually that there are collisions. Yeah. So, so it's so you can start to think of, okay, can I have, like, instead of having many atoms at per lattice site, can I start to think of working with less than one atom per lattice site? So yeah, that could be one solution, but then of course you have to start to think of, if this is the route that you like to go, you have to start to think of, then your atom number of course decreases, so which means your signal to noise ratio also decreases, and you could be detected, you could be limited by your detection capability. So you have to have very good detection if you like to take that route. Another thing is, then you can think of, okay, if I want to tackle this problem, I can think of having a very kind of like stable magnetic field and a small magnetic field, and I can apply small intensity. But if you apply small intensity, small magnetic field, then the another, I would say, like that you need to overcome, speed breaker or whatever you call it, that you need to have a longer integration time, which means you need to have very good clock laser, which has very long coherence time. And that is, if you have that, then okay, at least this route could be sorted out. And if you combine these two, then low atom number, long integration time, then you are good to go. And fortunately at PTB they have the best clock so far, clock laser, which is as like coherence time exceeding 10 seconds actually, and so it's less sub 10 millihertz line width it has got. So if you have if you have an institute which can have such a clock laser, then I think you can start to think of those challenges. You can start to think of that you can overcome those challenges. And utilizing such a clock laser, what you can achieve is actually for strontium 88 with low atom number filling per lattice site, you can achieve a line width less than a hertz, not only less than a hertz, but as narrow as 220 millihertz. It's quite clean line width, utilizing those parameters which are low intensity and low magnetic field, stable magnetic field. And then you can start to think of that you can really get a very, very good clock, and that's what happens. So if you look at it, this one, utilizing those parameters, the uncertainty this clock got was 2 parts in 10 to the power 17, so it became one of the best clocks in Europe. And in terms of precision, it achieved 3 parts 10 to the power 17. Remember, it started with, the aim was to get a precision of 5 parts in 10 to the power 17 and similar uncertainty 5 parts 10 to the power 17. And you could see that it has already exceeded its expectations, or at the aim it started with. So actually it turned out to be a very good endeavor in the end, and because PTB also has many other optical clocks, so you are at a very good place to do some even measurements, and utilizing other optical clocks at PTB. There was an isotope shift which was measured within 12 millihertz, and that's I would say a very, very good result. So you could kind of shorten the uncertainty which were put in on this one before by other people in the world. Now I would say, like, so this is about space optical clock part, which was within European consortium. Then it's a mini lattice clock. I'll just give you some sort of like information about it, which is part of this quantum hub. So idea is like to go low, to continue to traverse the path of where you can make things more robust, more compact, and less power hungry. And you still achieve a stability of -16 or better. And then you could see that idea, of course, is long-term vision is that it could be much smaller than human size, by and large. And so it fits within work package 8 of quantum hub package. It has because quantum hub is not about only building a clock, but it's also about tackling. As I said, it's about the creating enabling environment, which means tackling the problem holistically. So if you like to make something smaller and get integrated in the long term, you also start to think of building building micro comms. So there are comms, like Raphael said, nicely discussed yesterday. They are rack system. They are quite compact now compared to they used to be before. But there is another branch that people have been working based on microcom, and people think this could be one way to get things more miniaturized, get things more integrated in future. So there are two groups, University of Sussex and Southampton. They have been working closely in synergy with the work that is going on in Birmingham, for instance. And then, as I said, that somebody has to build these components. We are building, let's say, systems, and these are kind of components, lasers, and there is a based on VEXEL technology. There is a group in Strathclyde. They have been building these lasers, and the idea of these VEXELs is that you can build something which is very high power with narrow line width. So at the moment, I think they have achieved something like 1 watt for blue laser and hundreds of milliwatt, more than 100 milliwatt for red laser, but line width getting into less than kilohertz. And these are kind of natural line widths you can get based on this technology. So just to give you an idea, so idea of our miniaturized clock again is a modular system like it was in space optical clock. So you can start to think of like idea is, of course, you can just take it around using a car, and the idea is that you have an atomics package like in space optical clock. We had an atomics package where you could really cool the atoms down, and you can manipulate them, and then you have a separate clock laser which is coming from NPL, and you can have third module where you can have laser stabilization and other lasers placed there, and also power and electronics. And when you interface them well, all these three systems, then you have a frequency standard. The fourth system that you require if you want to make it a clock, which is a frequency comb. So this is if you have a nice car, then you can take it around. So that's the idea of this mini clock in Birmingham. Then IQ clock, I would not say it's just I wanted to highlight. Actually, there are 12 partners within it. We are one of them, and 6 academic partner and 6 industrial partner. Some people are already here. Michael is here. Rafael from Toptica is here, and there are. Helmut was also here actually, who is part of that one, University of Innsbruck, and I think Gregory also, I saw he was here. So there are many partners, I think, of this consortium actually who came here and spoke. So the idea again here is that 2 parts of it. One is to realize super radiance, and then you have heard enough, I think, about super radiance so far. And then another is industrial part, which is lattice clock, and then find an application together with British Telecom. So what is the status in Birmingham of this setup? It's very recent one. Yesterday only I got this photograph. It's a test setup that we have set up, which is on a breadboard. You could see very small chamber, and we have got better than, or at least the reading of these ion pumps is better than -11 vacuum. So we have achieved the vacuum. Now we will start to place the lasers around it and start to think of really cooling the atoms in this chamber. So that's I would say in Birmingham, that's more like a status of it. So we have got a basis really to build things around it. So vacuum system. As I said, I would also like to say, I think some of these people seem to be interested in it. What I'm going to say is, when you start to miniaturize it, you could see that in the entire setup, the chamber is so small, and most of the space is being taken by, look, it's these two pumps, and then you have an oven. You could see it's fairly bulky compared to the size of the chamber. So one of the ideas that we have been working in Birmingham is, can we really remove this part entirely? If I remove this part from here to here, then my system could be much smaller. And if I can remove or have only one chamber, then I can just put an ion pump just attached to the chamber. So my system will become even smaller. And if there was a way I could pump out this chamber, either having no pump or integrating pump in itself. Yes, sorry, please.
If you really care about no power supply, do you really need an ion pump? Get a pump or titanium sublimation is not enough?
So in this one, so this is an X-door pump. So it's a combination of both.
But maybe at some point you can check if you really need this ion pump.
So this is what actually I was coming to. So if there are pumps, we haven't tried it yet, so we don't know if it works. But if somebody has tried, we would be happy to learn about it. But if it becomes, let's say, gator passive pump in such a way that they become part of, let's say, chamber itself, for instance, or could be fairly compact, then you could see the entire setup. You can shrink down to slightly larger than your vacuum chamber, or as big as vacuum chamber, and you could see that you could reduce form factor by many orders of magnitude immediately, because then you don't require this kind of also you don't require the supporting system, and so you reduce it and make it more integratable. One of the ideas that we are thinking of in Birmingham, we have worked on it, can we remove this part? So we can't do so much about vacuum because we don't have expertise, but we can start to think, being an atomic physics, can we do something to do with atoms which could directly be integrated in chamber, which means we don't need so there will be Siemens slower coming here, which is not there yet. We are working on that one. Can we just remove this stage? And one idea that we came up with was, so if you have, let's say, an oven, this is the emission that you get, so it's a thermal emission, and the velocity components typically you get that we got was, you could see, can go up to something like 800 meter per second. While in a MOT, magnet optical trap, typically your capture velocity is somewhere here. It's around 50 to 80 meter per second. That's a typical number, I would speak. And so you could see that the number of atoms that's useful for you is only this. So most of these atoms actually are useless that you are emitting. You are not able to utilize them. And so you use massive power, you use lot of atoms going into your vacuum chamber or in your setup without being utilized. And now idea is, and that also of course decrease your lifetime of your mode. Idea is, can we bring this one to close to the zero velocity, which means within the band where mode is efficient, which means around 50 plus minus 50 meter per second. So we found out if you have a strontium oxide, if you work with the strontium oxide for instance, then you could see the velocity distribution is around 0. And so which means if you have 50 meter per second, you could see actually you are sitting on either side of your peak. So most of the atoms which you are emitting actually are immediately you could use it. So bigger fraction is something that you can directly use. So it is very efficient in that sense, we found out. Another thing that you could see that the emission is quite Gaussian compared to which is more like Boltzmann. Another important thing, so what we did was we took a strontium oxide in the same chamber and the mode was around 2 to 3 centimeter away from that one, and we just found out in our lab we had a pointer like this which was slightly more powerful, could go up to 100 milliwatt, and we just illuminated the sample using this normal 405 nanometer, and then we saw actually the vapors were coming out, strontium vapor, which we could detect using 461 nanometer laser fluorescence. Another interesting thing that we found was that normally because strontium has a low vapor pressure, so normally it is like you would see in any experiment if you are working, if it is your dispenser or an oven, and then the flange that you have just in line of sight is often covered with strontium, and it's the same case for ytterbium as well. And then it means there was this perception, at least in our group, that once strontium atom hit the wall, they just go and stick there. But it turns out the distribution, because it's Gaussian and it's around 319 degree Kelvin, which is kind of a room temperature. And typically your chamber is sitting on room temperature, which means there is rethermalization, something happening together with walls of the chamber, which means the atoms must be bouncing back and forth at least few times before they go and stick to the wall. And we confirmed that one by avoiding direct line of sight of these atoms to the chamber, and we found actually fluorescence we could see where we didn't expect the atoms unless they were colliding with walls and reaching there after collision. So this was, I would say, like interesting result from physics point of view. And now based on that one, such a simple thing, we found out actually we were able to trap around 4 million atoms in strontium 88, but then it was not everybody interested in strontium 88. People are interested in 87. Does it also work for 87? So actually it does work for 87 as well, and then we found out around 1 million atoms we were able to actually capture in our blue mode. And lifetime we found was around 500 millisecond. I think for a clock operation these are very good parameters that you, especially for mobile clock, if you like to set up, it has got very good potential. At least we were very excited about that one. Then we were contacted by this group, Masami Yasuda in Japan, and he did similar thing to ytterbium later on after we published our results, and he published those results in some Japanese paper, and it worked for ytterbium. So I think which is a great thing, I think, for the community, if we are able to build atom source based on such a system or such an idea, I think we can shrink down the form factor to a greater degree. Now this was more about like what we have been doing in Birmingham as part of the strontium activity, more applied to clocks. Now I would like to bring you back to little bit more commercialization side. This is how we started with Quantum Hub, and I would like you to think a quantum sensor, let us say clock, you could think of, you can think of as a system, but then the system is made of different things. So, you need laser systems like Toptica could supply to you. So, they are more like a component supplier in this respect. Of course, they can also build system. You can think of like we need electronics. So, electronics company which could be Toptica itself or some other company can supply you, or you have to build yourself. Then the vacuum system, that if you look at these things, these are all the components. So, you require supplier of these components if you want to build a market out of it. So, somebody has to continue to supply these components. It could be many in one, it means just one company doing everything, but have different brands. Typically, this is not the case. Typically, you have different companies supplying different things, and then you integrate them, which academia doesn't have. Academia is not in the place to really build something which is at the market level. So, it has to be an industry which becomes system integrator. So, you get different systems like your mobile phone, which is iPhone or any phone. Actually, most of the companies like iPhone, they are not component builders. They are typically actually a system integrator. So, they get different components from different companies and then they integrate there, and then that company is, let us say, iPhone for instance. So, similarly, there could be a company like Toptica, as if I understand well, Rafael could correct me, they are not only component supplier, but they are also aspiring to become system integrator in this case for instance, and then sell this product as a clock, as a product itself. Then of course, you have within this quantum sensor, you also have like in a clock, you have a clock laser, that could be a separate module which could be a component in itself. And then it could be part of a bigger system of course, wherever like if you have a network, somebody building computer network, then it's just one component sitting somewhere for instance. So, that is how what I would like you to start to think of, like you have the language that I wanted to actually like you to grasp was that you start to think of a component supplier, you start to think of a system integrator, you start to think of who is going to use it, end user. So, that is the kind of language. If you want to build something, you want to launch a new product, like you want to build a quantum industry, then you have to start to think of these type of terms. Who is going to invest money, who will buy? That may not be just enough. Then there is a methodology many people use. I think it started in the US, which actually I started to learn. This was a new language for me, but as part of this quantum hub, we started to learn this language and we are still learning. I think we are better than we were 5 years ago, but I would not say we are expert in it. So, what I learned, I am trying to give you also through this lecture. So, it is NABC, which means if I want to build, let us say, a clock and I say it is very good, society could benefit it, and I would like it to be available in wherever it is needed, so that we could do things better and society could benefit from doing those things better. Then what you start to think of, what is the need, what is the challenge I am going to solve. What is something that already exists cannot solve? What is that thing? So, what is the need that we are trying to address, and A is what is the approach? The approach I am going to take, let us say build a clock, should it be optical clock, should it be microwave clock, or should it be something else, or should it be hybrid for instance. Then what is the benefit, which means what would be the customer's experience in it. So, this is the language you start to think of. So, it is not a typical physics language, but if you want to build something which you like to translate your idea into the market, you have to start to consider that type of thing, and that is what we learned actually as part of quantum or we still learning. Competition. So, if you want to launch something in the market as an academia, actually we are not interested in commercial, we are only facilitator in that sense as an academia. Having industry on board, they are the people who will do it. But you have to start to think of the technology you work on, then where are you placed. So, this is the type of NABC matrix it is called, that you start to think of what is the competition. And competition need not be like from other supplier or other company, it could be just other different type of technology, conventional technology for instance. how you can do better than what is already available, for instance. So you start to populate these things, and then for instance, that I have already given you the example. This was based on the UK one, so like brownfield sites. So there are some issues there. Can I reduce the cost there, for instance? This could be a challenge I would like to solve. And can quantum technology solve it better than what is conventional one? Then you start to think of actually what I am going to produce. Is everybody going to be happy and adopt it? Once the experiences, are they going to adopt it? So that's sort of like when you start to think of these kind of then you start to think of bit more internally, rigorously, innovation and development process. What is going to be my innovation and development process? So that sort of, I think, answer you start to look for. And let me just I think bring out all of them just to give you, otherwise I think no, I think it's so it's as I said, you start to think of what is the need and who is going to use it widely, how it is, and then you start to populate it. For instance, okay, it may not be so easy for you. Then you start to look at the like different categories. You start to like open up a bit more and look at things more rigorously. Evaluate economic opportunity. Where are the economic opportunities? Technical feasibility. Is it feasible technologically or not? What should be the technical specification? And value chain and supply chain. That's what I wanted you to get a little bit idea, or at least start to think of in those terms. Supply chain and value chain. And then solution design. What should be the solution design in the end? So that's the language they start to speak. It might look bizarre, but actually this is how it. When you start to interface with industry end user, that's what the language they speak often. And then how to build it, and then where I'm going to do it, test and validate. So you require for clock, for instance, you require a metrology institute typically, or another for an optical clock, another optical clock to validate it. And then field trial, you need to go through field trial. You can build it, but then you have to prove that it works in field real world application. And then of course you analyze it and then you promote it, so engage with. So that sort of like a process you start to go into it, because somebody has to put money as well into the system. So I think I've already said about it. And then of course you require many times when you have a solution design, you have to have feedback and internal discussion and refine your approach. So I think when you have thought enough, then you start to think of like the people actually who could do these things. Like, okay, within the hub team they could do technical feasibility, they can also have solution design, they can also help with test and validation, field trial. But who are the other people who require, like civil engineers or people who work electrical engineers who might require timing, some component supplier, business school who could help us build the market. So that sort of things. And like for test and validation, as I said, Metrology Institute in the UK is a national physical laboratory. So all these things you start to think of like wider picture. It's not only you are sitting in a room and try to get the best result. I think that does not work completely here. And then you start to think of, as I said, technology roadmap, like different companies who could do what. So starting from, as I said, from component supplier to far end user who will use in the field. Not only that, some people would do consultancy based on the data. They would really help other companies what they can do or how they can use that particular system. So I think I would skip because it will be more and more boring. But what I wanted to say, that you start to think of all these considerations, and based on these ones, within our hub, we had a roadmap, and that was led our business director Simon Bennett, and there was some kind of like back of the envelope estimates, some sort of indicative, so not rigorous number. So if you look at these different themes within our hub, which is time, gravity gradients, magnetic field, what sort of market it might enable that it has quantum. So like timing 500 million, then gravity gradient could be 1 billion, and then health sector, magnetic field for instance 1 billion. So, there is a substantial argument why these activities should be taken. And what I discussed, so idea is like you start with component supplier all the way to the end user, which I have not put it here, but it should be somewhere on top of that one. So, you look at start holistic picture as I said before. So, I give you just one quick example of Teledyne E2V for instance, which is also part of IQ Clock consortium, and they are quite interested in quantum technology, and they are big company now. It's around 3 billion per annum. Now, question is like when you have such a big company doing very good business, why somebody should be interested in quantum technology? And most of the company don't understand what is quantum, because it's a relatively new idea. Why should they be interested? And why should they add, which they are already doing, why should they add a new thing to it? Is there a potential? And as I said, looking at those numbers which were in billions and millions, then of course there is a strong argument why people will start to consider being part of it and even taking up. And so they like to engage. For instance, these are 3 sectors they like to engage in quantum technology: gravity side, which means atom interferometers at the end of the day for physicists, and space, so quantum technology in space, and timing. Sorry for this one, I think it messed up for some reason, and clocks of course. So, these are the things they would like to build products, and this is where they are engaged. They have a lot of projects. Just to give you an idea, you could see these are projects which are quantum technology related projects, a number of projects they have been involved, and they have been working of course with different partners. As I said, it's not working alone need not be enough. When you start to think of, you have to look at much wider picture here. And they have a big team now, I think 20 plus people in their team. So, like just give you an example of timing. What they want is, if you look at the landscape, are they the only one? Is there no clock in the world? Actually, there are clocks already in the world. They are already working and based on atoms itself, like GPS. Every satellite of GPS has an atomic clock. And then there is a CSAC, which is chip scale atomic clock, can give you 10 to the power minus 9, it sits here, and then you could see there is a chain of course, and today what they want to sit on in one of their products is called MINAC. It's here 10 to the power minus 13, because it can capture a lot of applications. You don't need a better clock for a lot of applications, but there are of course clocks available which is HP5. They are expensive, but they are available sitting around the same region. And but this is in one of the products, this is where they want to sit. And then lattice clocks of course start to sit, like including IQ clock, they start to sit at the high end of the chain if you really see, but then the size also increases. So, you have to look at, you get better and better, but then size also increases. These are the things which are more like matchbox for instance, and can do a lot of jobs in these ones, and already works in real world. So, that is what they want to make their mark. These are still by and large in lab or fairly bulky, but advancement is happening. So, this project MINAC one, they have worked together with NPL, which is National Physical Laboratory. So, idea of this one is based on cesium. So, I think I need not go too much into details. The idea is that you can use 9.2 gigahertz microwave transition in cesium. It's a CPT clock, and you can build a very compact clock at the level of minus 13 or so. And it can, because it can make very compact, it's easy to carry around. So, this is where their idea is that they can demonstrate it and then make it in their product line. And these are the some of the considerations they always have to ask themselves as a company, like what they want to do, what sort of scale and sector, is there a potential market. This is one of the one of the first things actually companies think, where is the market? That is the first thing they come, who is going to buy it? Is the technology, how requirements captured, so how to capture the requirements, is technology to be used, which methods and limitations, do they have a capacity to do these things, and technology improvement compared to the current one, what is new it is bringing, what does not exist before, and what it can enable, what is the rationale behind it. So these are type of things I think every industry actually asks these questions before they start to think of let's say quantum technology in particular case. So of course in clocks they found out some of these this slide summarizes of their thinking that the clocks are important, and they are important for telecommunications. For instance, in the UK alone there are 500 base stations, but it could go up to 500,000. So there is a good potential there that there could be market, and this is for this type of clock. Of course they might like to have other type of clocks as well, but there is a good market here. Then science community, like astronomy, long baseline telescopes for instance, they require precision timing. Then experimental physics, like even standard labs for instance, some of them around the world might like to have them. Transport infrastructure, you might be bit surprised that rail network, there are 14,000 trains in the UK alone, and they do need actually timing. So there is a potential there. Air traffic control for instance, they also require timing. Then defense, they are interested if something happens to GPS or GNSS, they want to become independent of that one. And of course in a weaponry, which is of course not a good word for I would say for a school like here, but there is a market. This is how companies work. And then professional network, and based on those ones, the number they gave, they seem to have estimated around 230 million, which is a significant number. And that's why they want to go that way, that route. And then of course they start to think of like I just put them here because I'm running out of time, otherwise it's you start in what are the key drivers for the scientists. So first they have to engage with, because they don't have this capability in their in terms of knowledge, so they engage with academia, in this case NPL for instance, and somebody has to fund it, which typically government can fund it in some of the projects for instance. Then demonstrate together with academic people, demonstrate the feasibility of that particular concept, in this case CGM clock, MINAC which is called in their case. And then grant funding, of course de-risking, they don't have to put their own money, or part of the money they can get from somewhere else. Then what is the development model, is it variable or does it work? Then low volume, and then from there technology, when you start to think of this is a feasibility, that you build something as a prototype, and when they want to put in their production line, what are the considerations they have to go for? Is product for sale, is it profitable? It should be profitable. Engineer product, so it could be reproducible, so in the sense that you prepare a recipe and then people just start to put out copies of it. And then secure supply chain, as I said, is quite important. You are not going to do everything. And this is their target, as I said, is based on CGM clock, and that's what they would like. This is what MINAC target is. This line, bluish line, bit better than rubidium atomic clock, and push it down further. So this is where, as I said, like they would like to sit down with this their product line. Yeah. And then, as I said, like it's important for them what is the size, weight and power, which is called swap size. I think without boring you too much with this, you see that when you start to launch a product or you are serious about it, even as a company as big as Teledyne E2V, you start to think of different aspects and different people, different stakeholders. So it's a much bigger picture you need to consider, including supply chains, and these are the people that they have considered which are useful for their supply chain, and also knowledge transfer and test and validation. So I just want to literally in last couple of minutes, I just want to say this was about, I have mixed quite a lot of things, quantum technology initiative in the UK, mainly quantum sensor for quantum hub for sensor metrology, and some of the work that we have been doing in Birmingham. But there is another project that we have been setting up in my group, which I have not spoken, which is not directly related to clock, but it's more like I would say quantum simulation or long range interaction, where you can use many body, you can start to think of simulating many body Hamiltonian. It's also based on strontium. So idea there is quite simple in a way. So the idea is like you have a singlet state which is ground state in strontium, 1 is 0. And based on that one, then you have this clock transition which is 3p0. Typically you make a clock that you combine these two transitions, and then you do spectroscopy and you build your frequency standard and then a clock. So the idea is here, like, can we do something complementary to what Rydberg atom or ultra cold molecules could do? And the interesting part here is, like, if you take the idea of Rydberg atoms where you can get very large dipole moment, you have to go to very high excited states. Here idea is, can we use low lying states which are typically cleaner and are not so much influenced by the environment, like Rydberg atom is good to get large dipole moment, but it is also very sensitive to the environment that it actually works. Here that we use this 3D state which is very low lying and 3D 1 state, and can we use this this transition where it is 2.6 micron induced. So if you use this laser 2.6 micron laser, you can induce dipole moment as large as around 4 dBi. So which is very large dipole moment compared to, like, for instance, if you have a ultra cold molecule which is based on rubidium and potassium, then there is 0.5 dBi, for instance, just to give you an example, and this is and it's all neutral atom. So there is no, only difference is it's not a permanent dipole moment, it's a induced dipole moment. So what you can do, if you have a lattice which is spaced around 200 nanometer lattice site, so you have this atom at each lattice site. So what you can think of is this 2.6 micron laser wavelength is so large, then each atom here can interact with tens of other atoms on either side. So you can start to think of really doing something many body physics here, which is complementary to Rydberg atom. So we have started to set up this experiment. So where we are, we have set up actually in this experiment in a, it is not fully set up, but what we have got is a relatively new design of permanent magnet based Siemens slower, which are like magnet balls, and there we are able to get up to currently 1 billion atoms in blue mode. And as part of this one, that this setup functions very well. What we have measured is Landesi factor of 3D 1 state, which is roughly 0.5, agrees well with the theoretical values, and these are just some you could see components which is derived from, if you have a transition between 3D 1 state and 3p0 states, you could see plus minus 1 mf and 0 mf, this component, this is 0 1, this is minus 1, and this is plus 1, and deriving from that actually you can have nice physics results, which is measurement of Landesi factor. I think I just want to say this is not directly related to clock, but more many body physics that we could study using such a system. And this is the team actually that I lead, and we are still looking for some postdocs and actually few PhD students. So if someone you know and you're interested, most welcome. So this is the group that I lead, and I would say thank you very much. I still have 5 minutes if you like to ask any question.